everyone, myself Pavitra. I am here to present my AAT Tech Talk video of mathematical transform techniques. Today my topic is application of the Laplace transform in the solution of linear integral equations. Laplace transformation. What is Laplace transformation is to understand Laplace transformation, first we have to understand integral transformation. Integral transform maps an equation from its original domain into another domain where it might be manipulated and solved much more easily than in the original domain. The solution is then mapped back to the original domain using the inverse of the integral transform. So, Laplace transform is an integral transform named after its discoverer Pierre-Simon Laplace. It takes a function of a real variable t of n time to a function of a complex variable s. The Laplace transform is a useful tool for dealing with linear systems described by ODEs. The big deal is that the differential operator dy dx or d by dt is converted into multiplication by s. So, differential equations become algebraic equations that we will discuss later in applications. If f of t is a function of t for all t greater than 0, then integration of 0 to infinity e to the power of minus st f of t is dt is defined as the Laplace transform of f of t, provided integral exists and denoted by Laplace of f of t. Sufficient conditions for existence of Laplace transforms. First one, f of t is piecewise continuous function, and another one is limit t to 8 infinity limit e to the power of minus 80 f of t is equal to finite quantity t greater than 0. Laplace transform of elementary functions. By using 0 to infinity e minus st f of t dt, we can find Laplace transform of any function. Here are some standard Laplace transforms which can further be used to evaluate Laplace transform of other complex functions. Note that to evaluate Laplace transform, some special functions like gamma function, beta function, etc. are also used. F of t is equals to f of s is equal to Laplace of f of t. Tn is equals to n by Sn plus 1. EAT is equal to 1 by s minus a. Sin h of at is equals to a by s square minus a square. Cos h of at is s minus s square, s by s square minus a square. Sin at is equals to a by s square plus a square. Cos of at is equal to s by s square plus a square. Laplace transform of some basic functions. These are the Laplace transform of some basic functions. Now, basic properties of Laplace transform. Linearity, change of scale, first shifting theorem, second shifting theorem. Now, linearity, if Laplace of f of t is equals to f of s and Laplace of g of t is equal to capital G of s, then Laplace of a of f of t plus b of t is equal to a of f of s plus b of g of s, where a and b are constants. Change of scale. If Laplace of f of t is equals to f of s, then Laplace of f of at is equals to 1 by a f of s by a. First shifting theorem. If Laplace of f of t is equals to f of s, then Laplace of e to the power of minus at f of t is equals to f of s plus a. Second shifting theorem. If Laplace of f of t is equals to f of s and g of t is equals to f of t minus a comma t greater than a 0 comma t less than a, then Laplace of g of t is equal to e to the power of minus as f of s. Multiplication by t. If Laplace of f of t is equals to f of s, then Laplace of t to the power of n f of t is equals to minus 1 to the power of n d to the power of n by d to the power of sn f of s. Division by t. If Laplace of f of t is equals to f of s, then Laplace of f of t by t to the power of n is equals to integration of s to infinity n times f of s ds. Laplace transforms of integrals. If Laplace f of t is equals to f of s, then Laplace of integration 0 to t f of t is equals to f of s by s. Unit step function. Unit step function is defined as u of t is equals to 0 t less than 0 1 t greater than 0. Unit step function is also known as Heaviside function. Now, delayed unit step function can be defined as u of t minus t naught is equals to 0 comma t less than t naught 1 t greater than t naught. Laplace of f of t u of t minus t naught is equals to e to the power of minus t naught s f of s plus t naught, where Laplace of f of t is equals to s. Delayed delta function is now Laplace of f of t sigma t minus a is equal to e to the power of minus as f of s. Graph of delta function. Now Laplace of f of t delta t minus a is equals to e to the power of minus as f of a. This is the delta function. Animated explanation of delta function. Delta of t minus a is equals to 0, t not equals to 0. Next, integration of minus infinity to infinity delta t minus a dt is equals to 1, t is equals to 0. Inverse Laplace transforms. If Laplace of f of t is equals to f of s, then f of t is called the inverse Laplace transform of f of s. Mathematically, it is written as f of t is equals to L inverse f of s, where L inverse is called inverse Laplace operator. Note that f of t is the piecewise continuous and exponentially restricted real function. Inverse Laplace transforms of simple functions can be found from the properties of Laplace transforms. Basic properties of inverse Laplace transform. Inverse Laplace transform has all the basic operators which Laplace transform have linearity. If Laplace inverse f of s is equal to f of t and Laplace inverse g of s is equal to g of t, then Laplace inverse of af of s plus bg of s is equal to a f of t plus b g of t, where a and b are constants. Change of scale. If Laplace inverse f of s is equal to f of t, then Laplace inverse f of as is equals to 1 by a f of t minus a into a greater than 0. First shifting theorem. If Laplace inverse f of s is equal to f of t, then Laplace inverse f of s plus a is equals to e to the power of minus 18 f of t. Second shifting theorem. If Laplace inverse f of s is equal to f of t and g of t is equal to f of t minus a t greater than a 0 t less than a, then Laplace inverse of e to the power of minus as f of s is equal to g of t multiplication by s. If Laplace inverse f of s is equal to f of t, then Laplace inverse s f of s is equal to f dash of t is equal to d by dt of Laplace inverse of f of s. In general, Laplace inverse of s to the power of n f of s is equal to f to the power of n of t division by s. If Laplace inverse of f of s is equals to f of t, then Laplace inverse f of s by s is equal to integration 0 to t f of t dt. In general, Laplace inverse f of s by s to the power of n is equal to integration 0 to t, integration 0 to t, integration 0 to t n times f of t dt dt n times. Differentiation of transforms. If Laplace inverse f of s is equal to f of t, then Laplace inverse f of s is equals to minus 1 by t Laplace inverse of f dash of s. Sometimes it is hard to find inverse Laplace transforms directly. We can use this method to find inverse Laplace transform easily. For example, log trigonometric inverse functions. Integration of transforms. If Laplace inverse of f of s is equals to f of t, then Laplace inverse of f of s is equals to Laplace inverse of integration s to infinity f of s ds. This can be used for higher power terms in denominator. For example, 2 by s minus a whole cube. Partial fraction expansion. Sometimes given function has complex polynomials in denominator. In that types of cases, it is hard to find Laplace transforms of them. For example, s by s plus 1 into s minus 1 s square plus 1. Any function f of s can be written as p of s by q of s, where p of s and q of x are polynomials in s. To perform partial fraction expansion, the degree of p of s must be less than the degree of q of s. Assuming the degree of p of s is less than that of q of s, 4 possible cases arise depending upon the factors of q of s. Case 1. Factors are linear and distinct. F of s is equals to P of s by s plus a into s plus b. By partial fraction expansion, f of s is equal to a by s plus a plus b by s plus b. Case 2. Factors are linear and repeated. F of s is equal to P of s by s plus a into s plus b all to the power of n. By partial fraction expansion, f of s is equal to a by s plus a plus b1 by s plus b plus b2 by s plus b whole square plus so on up to bn by s plus b all to the power of n. Case 3. Factors are quadratic and distinct. F of s is equals to P of s by s square plus as plus b of s square plus cs plus d. By partial fraction expansion, f of s is equals to as plus b by s square plus as plus b plus cs plus d by s square plus cs plus d. Case 4. Factors are quadratic and repeated. Type equation here. F of s is equal to P of s by s square plus as plus b of s square plus cs plus d all to the power of n. By partial fraction expansion, f of s is equals to as plus b by s square plus as plus b plus c1s plus d1 by s square plus cs plus d plus c2s plus d2 by s square plus cs plus d all to the power of whole square plus up to cns plus dn by s square plus cs plus d all to the power of n. The constant coefficients can be found out by equating two sides equal and evaluating it. Thus, we can do partial fraction of given function and find inverse Laplace transform by linearity property. Convolution theorem. Laplace inverse of f of s is equals to f of t and Laplace inverse of g of s is equal to g of t. Then Laplace inverse of f of s into g of s is equal to integration 0 to t f of u g of t minus u du, where integration of 0 to t f of u g of t minus u du is equals to f of t into g of t. F of t into g of t is called convolution of f of t and g of t. Any of the given two functions can be chosen as f of t and g of t. Convolution of ODEs using Laplace transform. Solution of linear ODEs using Laplace transform. The Laplace transform is useful in solving linear differential equations with given initial conditions by using algebraic methods. Initial conditions are included from the very beginning of the solution. Before solving linear ODEs, we need to understand Laplace transforms of derivatives in general. Laplace of f of n of t is equals to s to the power of n f of s minus s to the power of n minus 1 f of 0 minus s to the power of n minus 2 f dash of 0 minus s to the power of n minus 3 f double dash of 0 up to so on f of n minus 1 of 0. From this formula, we can derive expressions for any derivative of f of t. Linear differential equation, Laplace transform, algebraic equation, solution of differential equations, inverse Laplace transform, solution of algebraic equation. Method for solving ODE. By following method in the above figure, we can solve any ODE easily. The drawback of this method is that f of 0, comma f dash of 0, comma f double dash of 0, etc. are required. Now, applications of Laplace transform. Basically, a Laplace transform will convert a function in some domain into a function in another domain without changing the value of the function. We use Laplace transform to convert differential equations having complex differential equations to relatively simple equations having polynomials. Since equations having polynomials are easier to solve, we employ Laplace transform to make calculations easier. We use Laplace transform on a derivative to convert into a multiple of the domain variable. Thus, with Laplace transform, nth degree differential equation can be transformed into an nth degree polynomial. One can easily solve the polynomial to get the result and then change it into a differential equation using inverse Laplace transform. Laplace transform is heavily used in signal processing using Laplace or Fourier transform. You can study a signal in the frequency domain. This can be a powerful tool. For instance, if your signal is smooth over time, it means that in the frequency domain you are very likely to find only small frequencies. Machine learning focuses on prediction based on known properties learned from the training data. Data mining of which is the analysis step of knowledge discovery in databases focuses on the discovery of previously unknown properties on the data, where Laplace equation is used to determine the prediction and to analyzes the step of knowledge in databases. Laplace transform has several applications in almost all engineering disciplines. Now, system modeling. Laplace transform is used to simplify calculations in system modeling, where large differential equations are used. Analysis of electrical circuits. In electrical circuits, a Laplace transform is used for the analysis of linear time invariant systems. Analysis of electronic circuits. Laplace transform is widely used for electronics engineers to quickly solve differential equations occurring in the analysis of electronic circuits. Digital signal processing. One cannot imagine solve DSP of digital signal processing problems without employing Laplace transform. Nuclear physics. In order to get the true form of radioactive decay, a Laplace transform is used. It makes studying analytic part of nuclear physics possible. Process controls. Laplace transforms are critical process controls. It helps analyze the variables which can alter, produces desired manipulations in the result. Now, for example, while study heat experiments, Laplace transform is used to find out to what extent the given input can be altered by changing temperature. Hence, one can alter temperature to get desired output for a While this is an efficient and easier way to control processes that are guided by differential equations. Now differentiation and integration of Laplace transform. Differentiation of Laplace transform. If Laplace of f of t is equals to f bar of s, then Laplace of t to the power of n f of t is equals to minus 1 to the power of n dn by ds to the power of n f bar of s, where n is equals to 1 comma 2 comma 3 so on. Integration of Laplace transforms. If Laplace f of t is equals to f bar of s and f of t by t has Laplace transform, then Laplace of f of t by t is equals to integration of 0 to infinity f bar of s ds. Evaluation of integrals by Laplace transform. Example, integration of 0 to infinity t e to the power of minus 3t cos t dt. Laplace of f of t is equal to integration of 0 to infinity e to the power of minus st f of t dt. S is equal to 3, f of t is equal to t cos t. Laplace of t cos t is equals to integration 0 to infinity e to the power of minus st t cos t dt. Laplace of cos t is equal to s by s square plus 1. Laplace of t cos t is equals to minus 1 by d by ds of s by s square plus 1 is equals to minus 1 of s square plus 1 minus 2s square by s square plus 1 whole square. Laplace of t cos t is equals to s square minus 1 by s square plus 1 whole square is equals to integration 0 to infinity e to the power of minus st t cos t dt. Integration of 0 to infinity e minus 3t t cos t dt is equals to 9 minus 1 by 9 plus 1 whole square is equal to 8 by 100 is equal to 2 by 25. Example, derivative Laplace transform of sin at. Let f of t is equal to sin at, then f dash of t is equal to a cos at and f double dash of t is equal to minus a square sin at. Also, f of 0 is equal to 0 comma f dash of 0 is equal to a. From this, Laplace of minus a square sin at is equals to s square L of sin at minus a. Minus a cube by s square plus a is equal to s square Laplace of sin at. Laplace of sin at is equal to a by s square plus a square. Example, minus Laplace of integration 0 to t cos u du. Solution, here f of u is equal to cos u. Laplace of integration 0 to t cos u du is equal to 1 by f bar of s is equal to 1 by s of s square plus 1. Thank you.